For decades, Mars has been the stage for humanity's greatest scientific dreams and its strangest conspiracies. But now, with the arrival of 3I Atlas, the third confirmed interstellar object, the red planet has entered the story in a way no one expected. Its flyby geometry, its timing, and its chemistry all hint at a peculiar connection to Mars. Is this coincidence or choreography? Tonight, we will explore this question slowly, carefully, one chapter at a time. Each segment will help us fall deeper into wonder, and perhaps into sleep. For as long as humans have looked to the skies, Mars has held a peculiar fascination. It is not the brightest planet. Venus gleams more brilliantly in the dawn, and Jupiter commands more mass and grandeur. Yet Mars, with its soft, ruddy glow, has always seemed closer to us. It is a neighbor that feels both familiar and strange, a world that reflects our own ambitions and anxieties back at us. The ancients named it after their gods of war. In Mesopotamia, it was Nergal, a deity of conflict and plague. To the Romans, it was Mars, fierce and red as spilled blood. Across cultures, its hue carried associations of danger, passion, and struggle. When people raised their eyes to the heavens, Mars stood out as the restless wanderer, a celestial body that did not follow the steady backdrop of stars, but roamed unpredictably through the night sky. To early stargazers, this roaming nature hinted at will, at agency, at something alive. As astronomy matured, Mars continued to play a unique role in our imagination. By the late 19th century, telescopes revealed faint lines crisscrossing its surface. Percival Lowell, an American astronomer, interpreted these markings as canals immense, straight waterways carved by intelligent beings. For decades, even as skeptics pointed to optical illusions, the idea persisted. Whole civilizations were imagined on the Martian plains, desperately building canals to preserve water on a dying planet. In truth, the canals never existed, but the narrative gripped the public mind. Mars became, in collective imagination, the first place in the cosmos where life beyond Earth might reside. This perception was not merely scientific curiosity, it reflected our own state of mind. At the dawn of the 20th century, humanity was wrestling with industrialization, empire, and looming conflict. The notion of an intelligent but endangered Martian civilization felt like both a projection and a warning, a mirror of our fears about scarcity and survival. Mars has continued to mirror our shifting hopes and fears ever since. In 1938, Orson Welles broadcast his famous War of the Worlds radio drama, Transforming H.G., Wells's novel into a live news-style report of Martians invading Earth. For listeners who tuned in midway, the story felt real. Panic spread briefly across American towns, reminding us how easily fear could be sparked by the idea of Martian others. The Red Planet, once a place of canals and fragile civilizations, had become a symbol of invasion, of the alien threat. Then came the space age. In the 1960s and 70s, robotic probes flew past Mars, revealing a barren world of craters, valleys, and dust storms. The myth of canal builders collapsed under hard data, yet the fascination endured. NASA's Viking landers of 1976 searched for microbial life, drilling into Martian soil and testing its chemistry. The results were ambiguous. One experiment hinted at biological activity. Others denied it. The mystery only deepened. Mars had refused to yield its secrets, and so we kept returning. By the 21st century, Mars became something different again. No longer only a canvas for alien fears, it became humanity's next great goal. Rovers like Spirit, Opportunity, Curiosity, and Perseverance have crawled across its landscapes, finding evidence of ancient rivers, lake beds, and minerals that form only in water. To scientists, these discoveries transform Mars into a natural archive of planetary history. To dreamers, they make it the next frontier of human settlement. Elon Musk and SpaceX speak openly of colonization. Space agencies design habitats and greenhouses. In Mars, we now see not only what might have been, but what might yet be a second chance, a backup home, a stage for humanity's expansion beyond Earth. Through all these transformations, Mars remains a mirror. In myth, it reflected our fears of war. In early astronomy, it reflected our hope for companionship. In popular culture, it reflected our anxieties about invasion. In modern science, it reflects our ambition for exploration and survival. So when an interstellar object like 3I Atlas sweeps past Mars, it collides not just with a planet, but with centuries of layered meaning. The red planet is not just another world. It is humanity's chosen other, a place we have always invested with significance. And if 3I Atlas interacts with Mars in any way, whether by geometry, chemistry, or coincidence, it inevitably entangles itself in our deepest stories. On July Honest, 2025, a faint smudge of light appeared in the southern skies above Chile. The discovery came not from a human gazing through a telescope, but from an automated system, the Asteroid Terrestrial Impact Last Alert System, or ATLAS. Designed to protect Earth from incoming asteroids, it quietly scans the heavens each night, comparing thousands of images in search of anything that moves against the background of stars. That night, its algorithms flagged something unusual. The object was moving too fast, much too fast. Within hours, astronomers realized that its path through the sky did not belong to any known asteroid or comet bound by the gravity of our Sunday. Its orbit was hyperbolic, with an eccentricity far greater than 1. In simple terms, this meant the object was not looping around the Sun like a planet or a familiar comet. It was passing through a traveler from the vast dark beyond our solar system. This was only the third time in history such an event had been confirmed. The first was 1I Oumuamua in 2017, a strangely elongated body that tumbled as it flew, accelerating slightly as though pushed by invisible hands. The second was 2I Borisov in 2019, a more traditional comet, its bright tail streaming as it approached the Sunday. And now, this third interstellar visitor designated 3I Atlas, in honor of the telescope that found it was here. Each of these visitors had been rare, fleeting, and enigmatic. But 3I Atlas, even in its first hours of observation, seemed different. Larger, faster, stranger. Its velocity was extraordinary, nearly 130, 0 miles per hour, or about 209, 0 kilometers per hour. To put that into perspective, a rifle bullet travels at less than 1,000 miles per hour. 3I Atlas was moving almost 200 times faster. At such speeds, it could cross the entire width of the continental United States in under 3 minutes. This sheer momentum alone set it apart. Whatever star system had ejected it, whatever gravitational slingshots it had endured along the way, 3I Atlas carried with it the energy of a distant past, preserved across billions of years of wandering. And yet, velocity was not its only signature. Observations from ground-based telescopes quickly revealed a coma, a hazy envelope of gas and dust surrounding the nucleus. That meant this was not a dead rock, but an active body, one that released vapor as sunlight struck its surface. The chemistry of that vapor defied expectations. Most comets we know are dominated by water. But 3I Atlas seemed to exhale carbon dioxide at a ratio far beyond anything seen before. A world of ice, but not like ours. A recipe written in a different stellar kitchen. Why does this matter? Because every interstellar object that passes through our solar system is more than a curiosity. It is a physical sample from another planetary nursery. Each carries clues about how planets form, how chemistry evolves, and how common or uncommon Earth-like environments may be. Our probes can travel only so far, our telescopes can only see so deep, but when an object like 3I, Atlas, comes to us, it is as if a fragment of another world has been hand-delivered to our doorstep. It matters, too, because these objects challenge our assumptions. They remind us that the galaxy is not empty. Every so often, a shard of alien geology drifts close enough to study, and each one is different. Oumuamua tumbled mysteriously, with no visible tail. Borisov behaved like a comet, but carried unusual proportions of carbon monoxide. And now, Atlas, glowing with a chemistry all its own, seems to suggest that the galaxy is filled with more variety than our theories can yet explain. Finally, it matters because of timing. 3I, Atlas is not just passing anywhere. Its trajectory threads a path between Earth and Mars, approaching the red planet more closely than its own moons. For astronomers, this is coincidence, written in orbital mechanics. For storytellers, it feels like choreography, as though the universe has chosen to send its emissary not just into our solar system, but into the very heart of our ambitions for exploration. A visitor from the stars is always significant. But when that visitor passes near Mars, the planet we dream of as our second home, the questions deepen. What can it tell us about other worlds? And what does its arrival say about our place in the larger story of the galaxy? 3. Atlas entered our solar system quickly, silently, and without warning. But in doing so, it became more than a point of light. It became a reminder that we are not alone in the universe's great machinery. We are part of a cosmos, still full of surprises, and sometimes the surprises come to us. The solar system is not chaos. It is a vast machine, its planets and comets and asteroids all moving in obedience to the same set of rules, carved into existence by gravity. From the elliptical path of Earth around the Sun to the subtle tug of Jupiter on distant comets, every orbit is part of an intricate, predictable ballet. Most of the time, this ballet feels distant, slow, and serene. But every so often, the steps align in ways that seem almost theatrical, as if the universe has staged a performance just for us. 3I. Atlas is one such performance. When astronomers first calculated its orbit in July 2025, the numbers told a remarkable story. Atlas was moving on a hyperbolic trajectory, meaning it came from beyond the Sun's reach, and once it passed, it would never return. This alone placed it in rare company, one of only 3 known interstellar objects to grace our skies. But the more interesting detail was where that trajectory carried it. The path of Atlas was not random. It threaded through the inner solar system with uncanny precision, passing close to Mars on October 3rd, 2025. Close, in cosmic terms, does not mean collision. At its nearest, Atlas would approach Mars at about 29 million kilometers. To us, that may seem impossibly far, but in astronomical context, it is intimate. Mars's own moons, Phobos and Deimos, orbit at just a few tens of thousands of kilometers. Atlas Pass, though much wider, would still bring it closer to Mars than many comets come to Earth. The geometry was perfect enough that orbiters circling the red planet would have a chance to capture images and data from a front-row seat, something impossible from Earth during that same period, when Atlas would vanish into the glare of the Sunday. This timing raised eyebrows among scientists. It meant that at the very moment Atlas was most active, sublimating gases and glowing with strange chemistry, Earth-based observatories would be blind. But Mars, the planet we have filled with robotic explorers, would be ideally placed. The choreography seemed almost too convenient. Our orbiters could become accidental witnesses to an interstellar visitor's closest brush with the Sunday. Was it mere coincidence? Orbital mechanics often produces alignments that feel uncanny. Gravity is impartial, and the solar system has had billions of years to spin its clockwork into place. But when an object from beyond our star system arrives on a trajectory that happens to weave so neatly into our neighborhood, it is hard not to marvel at the timing. To understand how Atlas found itself in this position, we must think of space not as emptiness, but as a river of gravitational currents. As Atlas fell toward the Sun, its speed and direction were subtly bent by the planets it passed, by the geometry of its incoming path, and by the immense pull of our star. Each influence acted like a nudge, shaping its dance through the solar system. The result was a trajectory that placed Mars, out of all the planets, at the heart of the show. Astronomers are careful not to read intention into coincidence. Yet history reminds us how easily humans do. For centuries, comets were seen as omens, their appearances tied to kings, wars, and disasters. Today, we know they are natural icy remnants from the birth of solar systems. But even with this knowledge, the sight of one threading so close to Mars feels symbolic. For scientists, it is a rare opportunity to collect data. For storytellers, it is choreography. A cosmic visitor bowing before the very planet humanity dreams of colonizing. The dance does not end at Mars. After its near pass, Atlas will swing inward, reaching perihelion on October 29, its closest approach to the Sunday. Then it will arc outward again, vanishing into interstellar darkness. Its entire performance, from discovery to departure, will last less than 2 years. But within that brief span, its steps seem carefully placed. Earth, blinded by sunlight. Mars, perfectly positioned. Robotic eyes ready to watch. Orbital choreography reminds us of 2 truths. First, that physics governs everything, the arcs of planets, the tilt of moons, the fleeting passes of visitors from the stars. And second, that even within those laws, alignments can feel like messages. They suggest meaning, even when none is intended. With Atlas, the dance brings it near Mars, and that nearness, whether by accident or design, forces us to ask, why here and why now? Astronomy is, at its heart, the study of geometry written in motion. Distances, angles, and curves traced across billions of kilometers all follow the same rules of gravity. Sometimes those rules give us a solar eclipse, when the moon passes directly between Earth and the Sunday. Sometimes they give us a planetary conjunction, when 2 worlds line up in the sky as if in conversation. And every so often, they give us something stranger. A visitor from another star system threading itself into the solar system's clockwork with uncanny precision. October 3rd, 2025, marks one of those moments. On that date, the interstellar object 3I, Atlas, will make its closest approach to Mars. It will not skim the surface, nor fall into orbit, nor threaten impact. Instead, it will pass at a distance of about 29 million kilometers, close enough to be remarkable, yet distant enough to pose no danger. In cosmic terms, this is a brush of shoulders at a crowded dance, a near encounter shaped entirely by the mathematics of hyperbolic motion. To imagine this, picture the solar system as a vast stage. Each planet traces its path with dependable rhythm, Mars moving at roughly 24 kilometers per second around the Sunday. Into this choreography comes Atlas, racing inward at more than 60 kilometers per second relative to the solar system. Its track is not circular, not even elliptical, but hyperbolic, a curve that dives close to the sun and then escapes forever into the dark. On October 3rd, the geometry of that curve brings it into Mars's neighborhood, close enough that the red planet becomes the best vantage point in the solar system for observing the interstellar visitor. Why does this geometry matter? because from Earth's perspective, the encounter is hidden. In early October, Atlas lies too near the sun's glare for our telescopes to see. To us, it disappears into brightness, unreachable by even the Hubble or James Webb Space Telescopes. Yet at the same moment, Mars is offset just enough in its orbit to view the passing object clearly against the backdrop of space. That means our robotic emissaries already circling Mars, the Mars Reconnaissance Orbiter, MAVEN, and even rovers on the surface communicating with orbiters above may glimpse Atlas in ways Earth cannot. The geometry is both limiting and generous, blinding us while granting Mars a privileged view. For scientists, this creates a unique opportunity. No other interstellar object has ever come so close to a planet with such an extensive fleet of instruments in place. High-resolution cameras, spectrometers, and even dust detectors may record its passage, offering data we could never gather from Earth alone. It is as though the cosmos has staged an experiment, arranging Atlas and Mars on converging paths for just long enough to exchange glances before parting forever. Yet, there is a more human layer to this geometry. For centuries, Mars has symbolized our curiosity about life beyond Earth. To see an object from another star sweep past the red planet feels like myth becoming reality. The war god's world meeting the emissary of distant suns, the dry deserts of Mars juxtaposed with the icy gases of an interstellar traveler. Even if no intention exists, the alignment resonates with meaning. The encounter is brief. At interstellar speeds, Atlas covers its closest approach in a matter of hours. By the next day, it will already be farther from Mars, on its way toward perihelion later that month. By December, it will re-emerge from the sun's glare into Earth's skies, a faint smudge once again. But for that single day in October, the geometry of space grants Mars the starring role in a cosmic alignment. What will we see? Perhaps nothing dramatic, just a dim object in telescopic frames, a comet-like haze recorded in spectral lines. Or perhaps something unexpected, a twist in chemistry, a flash of activity, a signature we do not yet recognize. The truth is that we cannot predict. The only certainty is the geometry itself. October 3rd, 2025, an interstellar visitor passing within 29 million kilometers of Mars, never to return. In the end, the significance lies not only in the data, but in the perspective. We live in a universe where stars fling shards of ice and rock into the dark, where gravity bends their paths across light years, and where, every so often, one of those paths intersects with our own. The close pass of Atlas near Mars is a reminder that cosmic geometry is more than mathematics. It is the language of encounters fleeting, silent, but filled with meaning for those who choose to look. When an object from another star system drifts into ours, its path is set long before it arrives. Gravity shapes every curve, every bend, every subtle shift. From the moment 3i, Atlas was ejected from its birth system, perhaps billions of years ago. Its future encounters were written into its trajectory. It would wander the galactic dark, slingshot past unseen stars, and eventually find its way here. And yet, of all the possible alignments, of all the planetary encounters it might have had, this object brushed closest not with Earth, but with Mars. On the surface, this seems like pure coincidence. The solar system is large, its planets tiny targets compared to the vastness of space. To hit Earth directly, or even to pass within a few million kilometers, would be almost impossibly unlikely. Instead, most interstellar visitors slip quietly through the outer solar system, far beyond our reach. Only a handful in history have passed close enough to detect it all. In that sense, the fact that Atlas comes anywhere near Mars is extraordinary in itself. But there's more to consider. Mars's orbit sits farther from the Sun than Earth's, at about 1.5 astronomical units. That extra distance places it in a different part of the solar system's gravitational web. When an interstellar object dives inward, the giant planets, especially Jupiter, exert powerful tugs that bend its path. These tugs can alter an approach just enough to bring the object near one inner planet rather than another. In this case, the gravitational choreography delivered Atlas to Mars's neighborhood. Nothing in the physics suggests intention. It is the outcome of mass and motion, blind and impartial. Still, the coincidence feels uncanny. For one simple reason: timing. At the very moment when humanity has populated Mars with orbiters, landers, and rovers, an interstellar visitor has chosen a path that favors the red planet as a vantage point. Earth, during the same weeks, is blinded by the sun's glare, unable to see the object at its most active. Mars, by contrast, is in just the right position. Its robotic eyes may capture data no Earth-based instrument can. It is as though the universe has handed the role of witness not to us directly, but to our machines on another world. This leads to an unsettling question. If Atlas had passed just a little closer to Earth, the encounter might have been far easier to study. Its coma and tail could have been tracked in detail by ground-based telescopes. Spectra could have been captured with unprecedented clarity. Instead, Earth is denied. Mars is granted. From a strictly statistical view, this is an accident, an outcome of orbital probabilities that could have gone either way. But from a human perspective, it feels like choreography. Some scientists note that Mars offers certain advantages. Its thinner atmosphere reduces interference for orbiting instruments. Its position in October 2025 provides a clearer line of sight to Atlas than Earth could manage. And its very status as a scientific outpost means we already have detectors ready. Perhaps this is simply the universe reminding us that exploration pays unexpected dividends. By placing instruments on another planet, we prepared ourselves unknowingly to observe a visitor from the stars. Of course, speculation creeps in. Writers and dreamers ask whether there might be more than coincidence here. If Atlas were not natural but artificial, if its path were shaped by intention rather than gravity alone, then choosing Mars over Earth might make sense. Mars is less crowded, less defended, yet filled with machines that will dutifully record and transmit data. To study humanity indirectly, without revealing itself too strongly, an encounter near Mars would be ideal. The scientific consensus, however, remains firm. Atlas follows the laws of physics. Its close pass with Mars is remarkable, but not miraculous. Still, in the quiet hours of observation, it is difficult not to reflect on what this alignment means. Why Mars and not Earth? The safest answer is chance. The deeper answer is that chance itself can feel like meaning. For billions of years, interstellar fragments have swept past the sun, unseen and unnoticed. Only now, in the brief window of human history when we can watch, do we see one pass so near to the very world we dream of visiting. Coincidence, perhaps. But coincidence of the kind that makes us wonder, if Earth cannot see, then who will watch? This is the question astronomers asked when orbital geometry revealed that 3I, Atlas, would reach its closest pass not under Earth's gaze, but in the skies above Mars. Fortunately, humanity has already stationed silent witnesses there, orbiters circling the red planet, patient machines designed for other tasks, but now positioned to observe an interstellar traveler in ways no telescope on Earth can. The most capable of these witnesses is the Mars Reconnaissance Orbiter, or MRO. Launched in 2005, it has spent nearly 2 decades circling Mars, mapping its surface in exquisite detail. Its high-rise camera can resolve objects less than a meter across from orbit, sharp enough to spot the tracks left by rovers as they crawl across the dust. MRO was never built to study interstellar comets. Its mission has been to study geology, monitor weather, and serve as a communications relay for landers below. Yet, in October 2025, it finds itself in a unique role, the closest sophisticated observer of 3I, Atlas, during its flyby. At a distance of roughly 29 million kilometers, Atlas will not appear as a world in the sky. To MRO, it will be a faint, moving dot against the stars. But faint dots can still tell stories. With carefully timed exposures, HiRISE may capture the subtle glow of its coma, the envelope of gas and dust released as solar heat strikes its surface. Filters can separate wavelengths of light, hinting at the chemistry of those gases. Even if resolution is limited, the presence or absence of certain signatures could confirm or challenge theories developed by Earth-based instruments before Atlas vanished into the sun's glare. Other instruments aboard MRO add depth to this opportunity. The CRISM spectrometer, although partially degraded, has experience mapping minerals and atmospheric particles. Pointed toward Atlas, it could extend its talents into interstellar space, analyzing reflected sunlight and emissions across multiple bands. Meanwhile, MARCI, the weather camera usually tasked with monitoring dust storms, might track the brightness variations of Atlas across time, revealing hints about its rotation or changes in activity. Perhaps most importantly, MRO is not alone. Other orbiters, MAVEN, with its instruments tuned for atmospheric escape, and the European Trace Gas Orbiter, built to sniff out methane in Mars's skies, could contribute their sensors to this improvised campaign. Each carries detectors sensitive to ultraviolet, infrared, or charged particles. Together, they form a small fleet of unplanned astronomers, circling Mars and looking outward, their gaze drawn not down to the red deserts below, but outward to a pale blur drifting through the dark. What makes this vantage point extraordinary is perspective. From Earth, Atlas is hidden by sunlight during much of its approach. From space telescopes near Earth, the same glare imposes a blind spot. But from Mars, the geometry shifts. Mars is offset just enough in its orbit that, for a narrow window of weeks, Atlas is visible against a darkened sky. It is as though Mars itself has stepped into a role standing in for us, hosting our emissaries as they record what we cannot. Will the orbiters succeed? The truth is, expectations must remain modest. Atlas will not blaze across the Martian sky. It will remain faint, dimmer than most stars visible to the human eye. Capturing it requires precision, coordination, and luck. And yet, if even a handful of frames reveal its coma, if even a spectrum shows its strange dominance of carbon dioxide, then those silent witnesses will have achieved something remarkable. The first interstellar object ever recorded from the skies of another planet. There is a quiet poetry in this. Our machines, launched decades ago for different purposes, now find themselves part of a story no one could have written. They orbit a barren world, loyal and uncomplaining, listening for signals and relaying whispers back to Earth. And in October 2025, they may capture a fragment of history, watching as an emissary from another star sweeps past. They will not speak. They will not interpret. They will simply observe, silently, as they always have. But in their silence lies a gift. Data carried across millions of kilometers, allowing us to glimpse what we could not see with our own eyes. The Mars Reconnaissance Orbiter and its companions will stand as witnesses to an encounter that belongs not only to scientists, but to all of humanity, proof that even in the vastness of space, we are capable of being present, even when the stage shifts to another world. Mars has 2 moons. They are not majestic like our own, rising full and bright above oceans. They are small, irregular, and dark, more like captured asteroids than proper worlds. Phobos, the larger, is barely 22 kilometers across. Deimos, the smaller, measures only about 12. Both are lumpy, scarred fragments, circling Mars like fragments of a broken crown. Yet these tiny companions may find themselves unexpectedly connected to the story of 3I, Atlas. On October 3rd, 2025, Atlas makes its closest approach to Mars, passing within 29 million kilometers. That distance dwarfs the orbits of Phobos and Deimos, which skim only tens of thousands of kilometers above Mars's surface. From their vantage points, the moons would see Atlas as little more than a dim moving star in the sky. But in astronomy, even faint points of light can carry meaning. Could Phobos and Deimos serve as observation posts? Not directly, for they hold no telescopes, no cameras, no instruments of their own. They are silent rocks, but their orbits host spacecraft, and spacecraft are the real keys to this chapter. The Japanese Aerospace Exploration Agency, JAXA, is preparing a mission called MMX, Martian Moons E-Exploration, designed to land on Phobos in the late 2020s and return samples to Earth. Though it will not arrive in time for Atlas's flyby, the mission illustrates how these moons are increasingly seen as stepping stones, convenient platforms from which to study both Mars and the wider cosmos. Phobos, orbiting just 60 kilometers above the Martian surface, completes a lap in under 8 hours. It rises and sets multiple times each day for anyone on Mars's ground. Deimos, farther out, moves more slowly, circling Mars every 30 hours. Together, they provide multiple perspectives on the Martian skies. A telescope stationed on either moon would enjoy an unobstructed horizon, free from the dust storms that often cloud the Martian atmosphere. With no air to scatter light, the skies above Phobos or Deimos are pitch black, ideal for observing faint interstellar visitors like Atlas. Astronomers have often imagined using such moons as natural observatories. A small telescope on Phobos, shielded from radio interference and with near constant line of sight to Earth, could serve as a deep space listening post. Deimos, with its slower orbit, could host instruments for longer, steadier observations. Neither world offers the stability of Earth's moon, but both are accessible in ways the Martian surface is not. In this sense, Atlas's flyby highlights a missed opportunity. We have orbiters around Mars, but not yet observatories on its moons. There is also the symbolic role to consider. Phobos means fear. Deimos means terror. In Greek mythology, they were companions of the god of war. For an object from another star to pass close to Mars, while its tiny moons look on, feels like a page torn from an ancient poem, an interstellar messenger drifting past while fear and terror circle silently overhead. Of course, in reality, Phobos and Deimos are indifferent. They will continue their orbits unchanged. But humans read meaning into alignments, and this alignment resonates with myth as much as with science. Still, even without instruments on the moons themselves, they may play a supporting role. Orbiters circling Mars often use Phobos and Deimos for calibration, snapping images of their surfaces to fine-tune cameras. If those orbiters attempt to track Atlas during its pass, the moons provide stable landmarks, reference points against which the faint interstellar object's position can be measured. In this indirect way, Phobos and Deimos help us see. The moons also remind us of scale. When Atlas brushes past at 29 million kilometers, that distance is more than 1,000 times farther than Phobos's orbit. To us, the difference between a few thousand and a few million kilometers can feel small, but in space, it is immense. Atlas is not aiming for Mars, nor for its moons. It is simply passing through, indifferent to scale, indifferent to witnesses. The fact that its path happens to align with Mars at all is miracle enough. Could Phobos and Deimos play a role in observation? Not as active participants. They are too small, too barren, too primitive. Yet they are part of the geometry. They are there, circling as they always do, silent companions to Mars, while an interstellar traveler sweeps past. And perhaps one day, when we have placed observatories on their surfaces, The next atlas will arrive, and the moons of Mars will become more than symbols. They will become true witnesses, small, dark eyes looking outward into the galactic night. If 3I Atlas had swept past Mars a century ago, no one would have known. The skies in 1925 were lit by telescopes that revealed only the faintest smudges, their optics unable to distinguish interstellar visitors from countless comets. If it had passed in 1825, it would have gone entirely unnoticed. In 1725, the very idea of an interstellar traveler would have seemed inconceivable. The truth is, timing matters. The meaning of an event is shaped not only by what happens, but by when it happens. And Atlas has chosen, or perhaps simply fallen, into a remarkable moment to arrive. For the first time in history, humanity has filled the orbit of Mars with a constellation of robotic eyes. The Mars Reconnaissance Orbiter has been circling since 2006, its high-rise camera mapping the surface in breathtaking detail. MAVEN watches the planet's atmosphere, studying how solar winds strip gases into space. The Trace Gas Orbiter from Europe and Russia hunts for faint signatures of methane, while older craft like Mars Odyssey continue to operate years beyond their design lives. Below them, on the surface, rovers crawl steadily across Martian terrain. Curiosity explores Jezero Crater, digging into its layered rocks for signs of ancient water. Perseverance, with its helicopter companion, Ingenuity, investigates Jezero Crater, caching samples that may one day be returned to Earth. These machines, scattered across Mars, form the most elaborate network of planetary observation humanity has ever constructed. And it is precisely now, during this golden age of Martian exploration, that 3I Atlas sweeps past. From a purely scientific perspective, the timing is fortunate. Earth itself will be blind during Atlas's perihelion passage in October, hidden behind the sun's glare. But Mars, offset in its orbit, will have the best vantage point. And unlike Earth, Mars has become an observatory world. Though no humans walk its soil, our instruments do. They are not passive machines. They are extensions of our vision. Their cameras, spectrometers, and detectors can record what our telescopes on Earth cannot. Timing has aligned their presence with the interstellar visitor's flight. This coincidence underscores a larger truth. Science advances not only by effort, but by luck. We built Mars orbiters to study geology, weather, and atmosphere. We did not design them for interstellar astronomy. Yet here they are, ideally placed to contribute. It is as though the cosmos anticipated our readiness, sending an emissary only when we had the tools to notice. The golden age of Mars exploration is also cultural. For the past 2 decades, Mars has dominated space policy, science fiction, and public imagination. It has become the planet of focus, the place where we test technologies, dream of colonies, and imagine second homes. Every rover launch sparks global headlines. Every new image of dusty landscapes feeds into a collective sense of connection. Against this backdrop, the arrival of 3I Atlas feels more than random. It feels narrative, as if the universe itself has added a chapter to the story we are already telling about Mars. Of course, from a scientific standpoint, there is no narrative. The trajectory of Atlas is a product of gravity, not intention. Its flyby is blind coincidence, yet meaning is something humans supply. The alignment of events, an interstellar object, the presence of our machines, the cultural moment when Mars stands as our next great frontier creates resonance. It turns a cold calculation into a story. The Golden Age will not last forever. Orbiters will fail. Rovers will fall silent. Funding will shift. But in 2025, everything converges. The sky above Mars is full of watchers. The surface is alive with explorers. And into that moment sweeps a visitor from another star, crossing paths with the one world we have chosen as humanity's second home. Timing is everything, and the timing of Atlas's arrival ensures that this fleeting encounter will not pass unnoticed. It will be recorded, analyzed, and remembered not as just another cometary passage, but as a chapter in the age when Mars became humanity's outpost, and the cosmos decided to stop by. From a purely scientific perspective, 3I Atlas is just another interstellar body, a shard of ice and rock ejected from its birth system, wandering for millions of years before crossing paths with ours. But humans rarely stop at the purely scientific. We ask why. We wonder about purpose. And one question keeps rising. If an advanced intelligence had wanted to study Earth without approaching directly, wouldn't Mars be the perfect place to watch from? The idea is simple. Earth is crowded, noisy, and filled with electromagnetic chatter radio, television, radar, and satellites, all screaming across the spectrum. Any object loitering too close would draw suspicion. But Mars is different. It is nearby, yet quiet. Its thin atmosphere does not blanket signals, its skies host no radio towers, and its orbit is just far enough away to keep observers hidden while still within range to study Earth. If you were looking for a discrete observation post in the solar system, Mars would be a candidate. This is the alien survey hypothesis, that Mars could serve as a safe vantage point for interstellar probes, not to announce themselves, not to interfere, but simply to watch. It is a hypothesis grounded more in imagination than evidence, yet it flows logically from our own strategies. When humanity studies distant planets, we do not land probes immediately. We orbit, we fly by, we observe from a safe distance first. Voyager 1 and 2 mapped the outer planets without ever touching their surfaces. Galileo orbited Jupiter. Cassini circled Saturn. The safest way to understand a new world is from afar. If we follow this logic, might not others? Mars's environment adds to the case. Its small moons, Phobos and Deimos, offer stable observation points in orbit. Its surface provides vantage points where instruments could be shielded from detection. And critically, its distance from Earth, roughly 55 million kilometers at closest approach, is far enough to avoid immediate notice, yet near enough to capture Earth's electromagnetic signals with relative ease. A sufficiently advanced civilization could study our transmissions, map our atmosphere, and track our technology, all without setting foot on our world. Of course, the scientific consensus remains skeptical. There is no direct evidence that Mars has ever hosted alien probes. Every rock photographed by rovers so far is just that, a rock. Every strange glint in an image eventually resolves into dust, sunlight, or lens artifact. Yet the hypothesis persists because it makes intuitive sense. If we would consider using Mars as an observation post, then perhaps someone else already has, and that is where 3I Atlas re-enters the story. Its path does not take it near Earth, but it does sweep past Mars. If it were artificial, and again, there is no proof of that, then its geometry would look deliberate. Earth is blinded by the sun during the critical weeks. Mars, however, is granted the clearest view. To human eyes, this alignment feels less like randomness and more like strategy. Even if Atlas is purely natural, the coincidence is striking. We are living through a golden age of Mars exploration, with orbiters and rovers in place to record its passage. We are also living through an age of global communication, where Earth's signals leak freely into space. For any potential surveyor, Mars is positioned as both shield and window, shielded from our suspicion, but open to our transmissions. Speculation aside, the alien survey hypothesis reflects something deeply human. It is less about evidence and more about projection. We imagine others acting as we would. We think of patience, reconnaissance, and strategy, because those are the qualities we value in exploration. Whether true or not, the hypothesis gives shape to our unease, the sense that if someone else is watching, they may already be watching from Mars. In the end, what matters is not whether Atlas is a probe, but what its presence near Mars suggests about our own mindset. We see Mars as a safe outpost, a staging ground, a place to watch from. And so, when an interstellar visitor brushes past that very world, we cannot help but wonder if we are seeing ourselves reflected, our logic, our methods, our curiosity echoed back from the stars. When astronomers pointed the James Webb Space Telescope at 3I, Atlas, in August 2025, they expected familiar chemistry. Comets in our solar system, after all, tend to follow a script. Water dominates, mixed with smaller amounts of carbon monoxide, carbon dioxide, and organics. This pattern reflects the conditions of the early solar nebula, the cloud of gas and dust from which our planets formed. But Atlas broke the script. Its chemistry was startling, almost alien in the literal sense. The data showed an astonishing carbon dioxide to water ratio of roughly 8:1. Instead of water vapor rising as the dominant gas, carbon dioxide streamed outward in quantities that dwarfed anything ever recorded in local comets. To put this into context, most comets in our solar system are water-rich. They are icy archives, their frozen surfaces releasing H2O when warmed by sunlight. Carbon dioxide is usually present, but secondary, a minor actor on the chemical stage. In Atlas, CO2 was the star. This finding was not only surprising, but also deeply resonant for planetary scientists. Because if there is one planet where carbon dioxide has always dominated, it is Mars. The Martian atmosphere today is about 95% CO2, thin and fragile compared to Earth's nitrogen-oxygen blend. Its red deserts are shaped not by oceans or forests, but by winds blowing through a carbon dioxide sky. Even its polar caps are layered with frozen CO2, the so-called dry ice that sublimates each spring, driving seasonal storms. Mars, in short, is the solar system's great carbon dioxide world. And here was Atlas, an interstellar visitor, carrying that same chemical fingerprint. Is it coincidence? Perhaps. The chemistry of comets is governed by where they formed in their birth systems. In colder, outer regions, water ice dominates. In warmer, mid-regions, carbon dioxide can condense instead. Atlas may simply be a fragment from such a zone, a place where CO2 snow fell more readily than water ice. But the resemblance to Mars invites reflection. Could environments like Mars be common across the galaxy? Are there countless worlds where carbon dioxide defines the landscape, where life, if it arises, must adapt to thin air and dry conditions? The carbon dioxide dominance in Atlas also hints at the processes of time. Exposed to cosmic rays for millions of years, ices can be chemically altered. Radiation may break down water molecules more readily than carbon dioxide, leaving behind a residue enriched in CO2. If this is true, then Atlas composition is not only a window into its birthplace, but also into the long, harsh journey it has endured between stars. Mars, too, has been sculpted by time once wetter, perhaps habitable, but over eons transformed into a dry world where carbon dioxide alone remains in abundance. This parallel deepens the mystery. When scientists describe Mars as a planet on the edge, they mean it hovers between what was and what could have been, between ancient rivers and present-day deserts. Atlas, with its chemical imbalance, feels the same. A body caught between two states, carrying the memory of a different environment, yet revealing itself in strange, unexpected ways. For those drawn to speculation, the parallel is tempting. If one wished to send a signal to Earth, how better than through chemistry that mirrors our own planetary neighbor? A ratio so extreme that it demands attention, and a fingerprint that echoes the one place we already dream of exploring. It may be nothing more than accident, but it feels like metaphor, a comet that speaks Mars language. Ultimately, the chemical clues remind us of scale. Mars is one example of a CO2-dominated world. Atlas may be another. And somewhere in the galaxy, there may be billions more. By studying one interstellar visitor, we are not just learning about a single icy fragment. We are glimpsing the possibility of planetary families, unlike our own families, where carbon dioxide, not water, writes the story of habitability. Atlas is not Mars, but its breath, heavy with CO2, reminds us that Mars is not unique. The chemistry of our red neighbor may be part of a larger pattern, woven across the stars. And if so, then Atlas has brought us more than data. It has brought us perspective, the hint that, in the great tapestry of planetary systems, Mars is not an outlier, but a chapter in a story far older and far wider than our own. When scientists examined the chemical outgassing of 3I, Atlas, they were struck not only by what it contained, but by what it seemed to echo. The faint, ghostly coma surrounding the interstellar visitor was dominated by carbon dioxide, a composition unusual for a comet yet strangely familiar. Because in our own solar system, one planet has always carried the same chemical signature: Mars. To compare Atlas with Mars is to compare two very different worlds. One, a frozen fragment from another star system. The other, a terrestrial planet that orbits quietly between Earth and the asteroid belt. And yet, chemistry ties them together. Mars's atmosphere is made up of 95% carbon dioxide, with only trace amounts of nitrogen, argon, and oxygen. Its thinness is legendary. Standing on the Martian surface feels like being nearly 35 kilometers above Earth's highest mountain. The air is so sparse that water boils away almost instantly, and even the strongest winds barely push against a rover's hull. Still, despite its fragility, that atmosphere is thick with CO2. Atlas, though not a planet, seems to exhale the same breath. Observations from the James Webb Space Telescope revealed a coma where carbon dioxide overwhelmed water vapor by a factor of 8 to 1. This is not just unusual, it is unprecedented in cometary chemistry. In effect, Atlas carries around itself an atmosphere that, in miniature, resembles Mars, thin, fragile, and dominated by carbon dioxide. What might this resemblance mean? On one level, it could be coincidence. The conditions that produced Atlas in its birth system may simply parallel those that shaped Mars. Perhaps it formed near the CO2 snowline of its original star, where carbon dioxide condensed more readily than water. Mars, too, sits in a precarious zone too small to hold on to its early water, too far from the sun to maintain a thick, Earth-like atmosphere. Both worlds may be the products of similar compromises in planetary chemistry. On another level, the echo invites deeper reflection. When we look at Mars, we see a planet caught between two identities, once wetter and warmer, now frozen and arid. When we look at Atlas, we see a comet that should have followed the water-rich script of its peers, but instead carries the dryness of carbon dioxide. Both tell stories of loss of atmospheres thinned, of water diminished, of environments where carbon dioxide dominates not by design, but by survival. For astrobiologists, the comparison raises questions. Could CO2-dominated environments be common across the galaxy? If Mars is not unique, if Atlas is not an anomaly, then perhaps planets with thin carbon dioxide atmospheres are everywhere. What would life look like on such worlds? Could microbes cling to the shadows of rocks, feeding on trace chemistry as scientists once speculated they might on Mars? Or does a CO2-heavy sky signal sterility, a stage where life struggles to begin? There is also the matter of habitability. On Earth, carbon dioxide is a trace gas, vital yet minor. On Mars, it is nearly everything, and its dominance is precisely why the planet is so inhospitable to us. Breathing the air would suffocate within moments. And yet, in our imagination, Mars remains the great target for colonization. To live there, we must reshape its atmosphere, bending its chemistry to our will. In this sense, Atlas is a reminder. It shows us that CO2 worlds may be natural, even common. The conditions we face on Mars may not be unique challenges, but universal ones, shared by planets scattered across the stars. Finally, there is the speculative echo. If an interstellar probe wanted to disguise itself, why not adopt a chemical signature that matches a nearby planet? A coma filled with carbon dioxide would seem less alien, more natural, when studied by astronomers who already know Mars. Again, there is no evidence for such intention, but the symmetry invites the thought. Does Atlas echo the thin air of the red planet? In composition, undeniably, yes. Both carry the imprint of carbon dioxide as their defining element. In significance, the answer is more subtle. The echo is a reminder that Mars is not alone, that our solar system's chemistry is not universal, and that perhaps thin, CO2-dominated skies are part of a galactic pattern. When we study Atlas's coma and Mars's air, we glimpse not just two isolated cases, but two expressions of a larger truth, that the universe writes its stories in rhyme. If you were an advanced intelligence drifting into a new star system, what would you study first? Earth, with its oceans, forests, and restless human civilization, seems like the obvious choice. It is vibrant, loud, and overflowing with data. But sometimes, the richest laboratory is not the busiest one. Sometimes, to understand a system, you examine the quieter parts. And Mars, dry, silent, and austere, may be the ideal laboratory. To humans, Mars is alluring precisely because of its paradoxes. It is dead, yet it hints at life. Its valleys and deltas tell of ancient rivers, yet its present atmosphere would boil water away in minutes. Its polar caps are layered with dry ice, but beneath them may lie briny lakes. Mars is a record of transformation from a wetter, warmer past to the desert we see today. For scientists, this transformation is a treasure. Studying Mars helps us understand planetary evolution, how atmospheres are lost, how climates collapse, how a world can shift from habitable to barren. For an intelligence far older and more advanced than us, these same qualities might be irresistible. A planet like Mars is a natural experiment already in progress. It shows what happens when water-rich conditions decay. It demonstrates how solar radiation, weak gravity, and atmospheric escape shape a world over billions of years. If Earth represents what is alive, Mars represents what has been lost. Together, they form a comparative data set. One planet still vibrant, the other faded. To a cosmic surveyor, that contrast could be more valuable than Earth alone. Mars is also a safer laboratory. Earth is noisy with technology. Any probe approaching too closely risks detection, confrontation, or even destruction. Mars, by contrast, is quiet. It is home only to our machines, which obediently record whatever they see and transmit the data back to Earth. An observer near Mars could remain unnoticed, studying our behavior indirectly. In that sense, the red planet is not only a geological archive, but also a convenient blind spot, a stage where science can unfold without interference. Beyond safety, Mars offers stability. Its surface is geologically ancient, scarred but largely unchanging. Unlike Earth, where erosion, plate tectonics, and vegetation erase the past, Mars preserves its history. Craters remain crisp for billions of years. Dried riverbeds remain etched in the sand. To scientists, human or otherwise, such stability is priceless. It is a record book that never burns, a set of experiments frozen in time. There is also the allure of extremity. Mars is hostile, yet not utterly alien. Temperatures swing from minus 100 degrees Celsius at night to just above freezing at noon. Dust storms cloak the planet for weeks, sometimes encircling it entirely. Radiation beats down on its unshielded surface. For us, these conditions are obstacles. For an advanced intelligence, they may be variables in an experiment. How does complex chemistry behave under constant radiation? How do dust particles shape climate? How do thin atmospheres preserve or erase signs of life? Mars answers questions Earth cannot. Perhaps most intriguing is Mars's potential as a testing ground. Humanity dreams of terraforming, thickening its atmosphere, melting its ice caps, seeding it with green. To us, it is a challenge for the far future. But to a civilization older and wiser, Mars might serve as a sandbox, a place to experiment with planetary engineering, a world where changes can be tried, monitored, and abandoned without consequence to any existing biosphere. If Earth is a garden, Mars is a laboratory bench. Of course, there is no evidence that 3I, Atlas, or any other interstellar visitor is interested in Mars in this way. The flyby may be pure coincidence, a trajectory carved by chance. But coincidence does not erase possibility. The fact remains, if one wished to study a solar system discreetly, safely, and deeply, Mars would be the ideal starting point. Mars is not only a planet. It is a record of change, a canvas of extremes, and a window into both past and future. To us, it is a destination. To an advanced intelligence, it might be a laboratory, a place to ask questions that Earth, with all its noise and life, cannot answer. For more than a century, Mars has been imagined not only as a place to visit, but as a place to transform. Science fiction writers dreamed of greening its deserts, thickening its air, and turning the red planet into a second Earth. In recent decades, those dreams have shifted from speculation to serious proposals. Engineers sketch out blueprints for habitats under domes, atmospheric processors, and space mirrors. Entrepreneurs speak openly of colonies. Governments fund studies on long-term human survival beyond Earth. The vision is bold, almost audacious. To terraform Mars. Terraforming means reshaping an entire planet to resemble Earth more closely. On Mars, the main obstacle is its thin atmosphere, dominated by carbon dioxide. At less than 1% of Earth's surface pressure, it cannot hold heat, cannot sustain liquid water, and cannot support human lungs. To make Mars habitable, that atmosphere must be thickened and warmed. And here is where 3I, Atlas, enters the story. When the James Webb Space Telescope measured Atlas's chemistry, it found something astonishing, a coma dominated by carbon dioxide, with an 8-to-1 ratio over water vapor. In other words, Atlas is an interstellar body that exhales precisely the gas humans would need to manipulate in order to terraform Mars. Carbon dioxide is a greenhouse gas. On Earth, in excess, it drives climate change. On Mars, in abundance, it could be a tool. Release enough CO2 into the Martian atmosphere, and the planet might warm. Ice could melt, seas could form, and air pressure could rise to levels more hospitable for life. It is tempting to see resonance here, the echo of our dreams in the chemistry of an interstellar visitor. Of course, Atlas is not a terraforming device. It is a comet-like body whose CO2 dominance reflects the conditions of its birth system and the scars of its long journey. Yet, the parallel is striking. As humanity contemplates reshaping Mars by unlocking trapped carbon dioxide in its soil and polar caps, Atlas drifts past, whispering of worlds where CO2 was always dominant. This raises deeper questions. If Atlas represents the kind of chemistry common in other planetary systems, then Mars-like conditions may be widespread. Perhaps many worlds in our galaxy are already CO2 planets, cold, thin-aired, and hostile to complex life. If so, terraforming may not be unique to Mars. It may be the universal challenge for civilizations, to take carbon dioxide skies and bend them into something more life-friendly. In this sense, Mars is not just our laboratory, but our initiation into a galactic problem set. Some thinkers go further. They imagine importing volatiles to Mars' comets redirected, asteroids captured, ices delivered to thicken its air. Atlas itself, with its CO2-rich chemistry, almost seems like the prototype for such cargo. If humanity could one day harness bodies like Atlas, nudging them into controlled impacts or processing their gases in orbit, terraforming might accelerate. What is now a fantasy could become an engineering project, aided by resources drifting in from other stars. Of course, the scale of such endeavors is immense. Releasing enough CO2 to thicken Mars's air to Earth-like levels would take centuries, perhaps millennia. Even then, Mars lacks a global magnetic field, so its atmosphere would continue to leak into space. Terraforming is less a single act than an ongoing struggle against physics itself. Yet, Atlas reminds us of possibility. Its presence proves that CO2-rich worlds exist beyond our solar system. If nature can make them, perhaps intelligence can remake them. In the end, humanity's terraforming dreams are not about Mars alone. They are about survival, resilience, and imagination. They reflect our refusal to be confined to a single planet, our determination to shape environments to fit our needs. Atlas, with its alien chemistry, drifts through our system like a mirror of those ambitions. It is not here to help us terraform Mars, but in its passing, it reminds us that the resources, the gases, and the possibilities are out there waiting. When we think of life, we think of water. On Earth, every organism depends on it. Our bodies are mostly water. Our climate is shaped by oceans, clouds, and rain. And when scientists search for life beyond Earth, their first question is almost always the same. Where is the water? Mars once seemed an obvious candidate. Telescopes in the 19th century suggested canals and seas, fueling dreams of an inhabited world. Later missions dispelled those illusions, yet still revealed evidence that water once flowed freely there. Dried riverbeds, sedimentary layers, and minerals that form only in liquid water told the same story. Billions of years ago, Mars was a wetter, warmer place. Today, however, its surface is dry. Only thin traces of vapor linger in the air, while ice hides beneath the soil and caps the poles. The puzzle is not whether water existed, but why it disappeared. 3I Atlas carries a similar puzzle, though in miniature. When astronomers examined its outgassing with the James Webb Space Telescope, they expected to find water vapor as the dominant component, as in most comets. Instead, they found the opposite. Carbon dioxide overwhelmed water 8-1. The absence of water was almost as striking as its presence. Here was an interstellar visitor, glowing with activity far from the sun, but exhaling hardly any H2O at all. This chemical imbalance forces us to ask the same kind of questions we ask about Mars. Was water once abundant in Atlas, only to be lost over time? Did cosmic rays strip it away during millions of years in interstellar space, leaving CO2 as the survivor? Or was Atlas always water-poor, formed in a region of its natal star system where water ice could not condense? The missing water is a clue, a fingerprint of history, but one that remains incomplete. The parallels with Mars grow deeper when we consider the implications. Both Mars and Atlas tell stories of water denied. On Mars, the air pressure is so low that liquid water is unstable. Even if ice melts briefly, it evaporates or refreezes within minutes. On Atlas, the very chemistry seems to exclude water, leaving a signature dominated by carbon dioxide. In both cases, water is absent where we might expect it, leaving only traces and questions. For scientists, these absences are not disappointments but mysteries. Mars's dry river valleys suggest a lost climate, one that might once have been habitable. Atlas's weak water signature suggests a birth environment different from our own solar system, perhaps around a colder or older star. Each absence is an opportunity, a window into conditions we cannot directly observe. For dreamers, the absence feels symbolic. Mars, the planet we hope to colonize, withholds the one resource we most need. Atlas, the visitor from the stars, carries a chemistry that seems to mock our expectations. Both remind us that water, though common, is never guaranteed. Life depends on it, yet the cosmos often denies it. Still, there are hints of persistence. Mars retains ice beneath its poles and in hidden reservoirs underground. Atlas, though CO2-rich, still shows traces of water in its spectrum. Neither is entirely devoid. Perhaps that is the greater lesson, that water survives even in hostile conditions, even when diminished. And so we are left with a dual puzzle. On Mars, where did the water go, and how much remains hidden? On Atlas, was water ever abundant, or was it scarce from the beginning? The answers matter not only for planetary science, but for the broader question of habitability. If Mars and Atlas are typical, then water-rich environments may be rarer than we hope, fragile oases in a galaxy filled with dry worlds. Both worlds whisper the same truth. Water is precious, precarious, and never promised. Its absence is as telling as its presence. And in that absence, we see a reflection of our own fragility, a reminder that what sustains us on Earth is far from universal. When we look at Mars today, we see a frozen desert. Its sky is thin, its soil dry, its air almost entirely carbon dioxide. Yet, scattered across its surface are unmistakable signs of a different age. Channels carved by flowing rivers, delta fans shaped by standing lakes, and minerals that can only form in the presence of liquid water. Billions of years ago, Mars may have looked more like Earth-blue skies, shallow seas, and climates that cycled through warmth and rain. The Mars of the past was not the Mars we see now. It was something else, a world of potential. Now imagine a different star system, far away, billions of years ago. Imagine that around one of its planets, not unlike Mars, ice condensed, rivers flowed, and climates shifted. And imagine that fragments of that ancient system were torn free during the chaos of planetary formation or the death throes of a nearby star. One of those fragments, flung into interstellar space, could be what we now call 3I, Atlas. This speculation raises an extraordinary question. Could Atlas be carrying material from a planet that once resembled Mars? There is no direct evidence for this, of course. Atlas shows no sign of being a planetary fragment. Its coma, chemistry, and behavior point to cometary origins. But the idea remains intriguing because of the parallels. Mars's story is one of change from habitability to barrenness. If Atlas came from a similar world, its chemistry might preserve echoes of those ancient environments. The unusually high carbon dioxide ratio could be a clue, hinting at a planet where CO2 dominated after water had diminished, much as it did on Mars. Planetary ejection is not rare in the universe. During the early history of star systems, gravitational interactions fling material outward with violent force. Some fragments collide, others spiral inward, and a few are cast into interstellar exile. These refugees, shards of planets, moons, or comets, wander for billions of years. When one of them crosses paths with another star system, as Atlas has with ours, it brings with it a sample of ancient history. Each interstellar visitor is a messenger, carrying a chemical memory of its origin world. For Mars, the connection is personal. Our studies of its rocks suggest that conditions there may have once been favorable to life. If Atlas originated from a similar Mars-like planet, then perhaps the galaxy holds many such worlds, planets that begin with water and warmth, only to lose both as atmospheres thin and climates collapse. Mars is our local example. Atlas may be a galactic reminder. There is also the possibility of deeper resonance. Some researchers speculate that interstellar objects could serve as panspermia vectors, carrying organic molecules or even microbial life between star systems. If true, then Atlas might not only echo Mars's ancient chemistry, but also preserve traces of biology from another world. This is not the scientific consensus so far. No life has been found in comets, interstellar or otherwise. But the possibility lingers at the edge of speculation. A Mars-like planet in another system, life beginning in shallow seas, fragments cast outward, drifting across the stars, one of them passing near Mars itself billions of years later. Even if Atlas is purely natural, the parallel is powerful. Mars reminds us that worlds evolve. They begin with promise, but time, gravity, and radiation shape them into something else. Atlas may be the frozen remnant of a similar process, a piece of a planet that once had its own rivers and skies. When we look at it through telescopes, we are not just studying a rock. We are glimpsing the possibility that Mars's fate from wet to dry, from fertile to barren, is not unique but common across the galaxy. Could Atlas carry material from planets that once resembled Mars? Perhaps not literally, but in its chemistry, in its CO2 dominance, and in its ancient wandering, it reflects the same story. The fragility of habitability, the inevitability of change, and the reminder that Mars is part of a larger pattern written into the stars. Light carries information. When it passes through a gas, certain wavelengths are absorbed while others pass freely. When that gas is heated, those same wavelengths can be re-emitted, leaving behind a fingerprint, a spectral signature that astronomers can read across millions of kilometers. This is how we know the composition of distant stars, the atmospheres of exoplanets, and the gases streaming from a comet's coma. It is also how we learn the most peculiar fact about 3I. Atlas. Its breath is dominated by carbon dioxide. Spectroscopy revealed not just a hint of CO2, but an overwhelming presence. The James Webb Space Telescope measured emissions where the characteristic absorption bands of carbon dioxide stood out with startling clarity. At a distance beyond Mars's orbit, Atlas was already glowing with activity, releasing carbon dioxide in volumes far greater than water vapor. This is unusual. For most comets, water dominates. Once they pass within a few astronomical units of the Sunday, carbon dioxide usually appears as a secondary feature. But in Atlas, CO2 is the main actor. This unusual chemical fingerprint immediately called to mind another world, Mars. For decades, Mars' atmosphere has been studied with the same tools of spectroscopy. Orbiters, landers, and telescopes have recorded its thin air again and again, finding the same result. Carbon dioxide dominates, accounting for 95% of its composition. The spectral lines that define Mars's atmosphere, the fingerprints of CO2, are among the strongest and most familiar features in planetary science. Here, then, is the resonance. Two very different bodies. One, a rocky planet in our solar system, the other an interstellar visitor, both speaking the same spectral language. Both reveal carbon dioxide as their defining chemical note. It is as if Mars and Atlas are mirrors, reflecting each other's signatures across millions of kilometers. Why does this matter? On one level, the resonance may be purely coincidental. The chemistry of Atlas comes from its formation, shaped by temperatures and pressures in a star system we will never see. The chemistry of Mars comes from its size, gravity, and distance from the Sunday. The two worlds have nothing in common beyond physics, and yet, in their spectra, they rhyme. To a scientist, such rhymes hint at universality, conditions that repeat across space, patterns that emerge in very different environments. If carbon dioxide dominates both Mars and Atlas, perhaps CO2-rich worlds are common. Perhaps the galaxy contains countless dry planets and icy bodies that speak this same spectral language. But resonance invites more than scientific comparison. It invites speculation. What if this similarity is not coincidence, but signal? If an advanced intelligence wished to be noticed, one method could be to echo something familiar. Earth is too crowded, too complex. But Mars, the quiet neighbor we study most, is already etched into our imagination. To produce a spectrum that mirrors Mars would guarantee our attention. It would feel like a message written in light, coded in chemistry, delivered through resonance. Of course, there is no evidence that ATLAS is anything but natural. Yet the timing, the geometry, and the chemistry combine into a pattern that feels almost theatrical. Mars, our chosen second home, is a carbon dioxide world. Atlas, passing closest to Mars, exhales carbon dioxide in unprecedented amounts. The alignment is not proof of design, but it is enough to stir the human mind, always eager for meaning. In the quiet hum of data, we hear the resonance. Spectral lines repeating across worlds, across systems, across time. Mars reflects the past, a planet that lost its water, leaving carbon dioxide behind. Atlas reflects the distant, alien present, a fragment formed under unknown skies, but carrying the same chemical tune. Together, they remind us that science is not only about measurements, but about patterns, and the wonder those patterns inspire. In the end, the mirror may be nothing more than coincidence. But sometimes, in astronomy, coincidence is the most powerful teacher. It shows us that our local truths are not isolated, that Mars's story is not unique, and that across the galaxy, other worlds may share its fate. The resonance between Mars and Atlas is not only spectral. It is symbolic, a reminder that in the vast silence of space, even distant objects can speak the same language of light. When astronomers look at distant objects, they do not hear voices. They do not receive neatly packaged messages. Instead, they study the faintest of clues, the way light bends, the way gases glow, the way molecules leave their fingerprints on spectra. Communication, in astronomy, is almost always indirect information carried not by intent, but by physics. Yet with 3i, Atlas, a question arises. What if chemistry itself could serve as a kind of signal? The evidence is clear. Atlas exhales carbon dioxide in proportions far beyond what comets in our solar system display. The James Webb Space Telescope measured a ratio of carbon dioxide to water vapor of 8:1, an unprecedented imbalance. In any normal comet, water vapor dominates. In Atlas, water is nearly drowned out by CO2. To planetary scientists, this means Atlas likely formed under different stellar conditions. But to those willing to speculate, it looks almost intentional, as if Atlas is broadcasting its difference in a way that we cannot miss. Why carbon dioxide? On Earth, CO2 is one of the most studied gases. It defines our climate discussions, our industrial footprint, and our models of habitability. On Mars, CO2 is the air itself, a constant reminder of a world that once might have supported life, but no longer does. To detect carbon dioxide is to immediately think of planets, atmospheres, and the question of life. In this way, CO2 already functions as a universal symbol not of life itself, but of the conditions that shape life. If one wished to leave a signature recognizable across civilizations, it would make sense to choose a molecule that is both simple and universal. Carbon dioxide fits that description. Its spectral lines are strong and unmistakable. Even primitive telescopes can detect it in planetary atmospheres. It cannot be confused with more obscure molecules. and because it contains both carbon and oxygen, two of the universe's most important elements, its presence is almost always relevant to discussions of biology. Could CO2, then, be a deliberate marker, a kind of chemical beacon? The idea is speculative, but it is not entirely new. Scientists in the search for extraterrestrial intelligence, SETI, have long debated whether advanced civilizations might use natural phenomena, rather than radio signals, as communication channels. Some suggest that unusual chemical ratios in comets or exoplanets could serve as breadcrumbs, clues left in plain sight. Not messages in the way humans speak, but signals in the way nature speaks, through imbalance, anomaly, and resonance. Still, caution is essential. Nature itself produces imbalances that can look artificial. Radiation can erode water ice more quickly than carbon dioxide, enriching a body's surface layers in CO2. Dust mantles can trap water below while letting CO2 escape. Formation zones in protoplanetary disks can produce volatile distributions unlike anything in our system. To leap from anomaly to intention is risky, and yet anomalies are exactly what catch our attention. They force us to ask questions. They make us look closer. Perhaps that is the true power of CO2 as a signal. Even if Atlas is entirely natural, its chemistry communicates. It tells us that our models are incomplete, that our assumptions are provincial. It tells us that the galaxy may hold countless bodies with chemistries we have not yet imagined. It tells us, simply, that we still have much to learn. Communication, in this sense, does not require intent. It happens whenever the universe surprises us, but speculation lingers at the edges. If 3I, Atlas, were artificial, if its path past Mars were intentional, then a CO2-dominated coma would be the perfect disguise. It would look natural, yet unusual enough to spark curiosity. It would not scream of technology, but whisper of difference. It would be subtle, but effective, a coded signal hiding in plain sight. Is CO2 itself a message? Perhaps not in the way we usually mean, but in the language of astronomy, where light and chemistry are the only voices we hear. It may be as close to a message as we will ever receive. Atlas speaks through its emissions, and what it says over and over is carbon dioxide. When we imagine our solar system, Earth naturally takes center stage. It is where we live, where life thrives, and where technology flourishes. But from the perspective of a visitor, an interstellar object sweeping inward at unimaginable speed, Earth may not be the most convenient focal point. Too close, and you risk collision or immediate detection. Too far, and you lose the ability to study its signals in detail. In between lies Mars, a middle ground, perfectly balanced between proximity and distance. Mars occupies a unique position. At 1.5 astronomical units from the Sun, it is close enough to Earth to observe us with clarity, but far enough to avoid our interference. The average separation between the two planets is about 225 million kilometers, a distance vast in human terms, but trivial for instruments capable of gathering electromagnetic data. Earth's radio leakage from television broadcasts, radar, and satellites spills out into space, expanding in all directions. Mars sits close enough that a patient observer could listen. For an interstellar traveler like 3I Atlas, this geometry matters. On its trajectory, Earth is hidden in the glare of the Sun during much of its approach. Mars, however, is offset just enough in orbit to enjoy a clearer view. The result is an alignment that feels almost staged. Earth blinded, Mars illuminated. If one were seeking a neutral vantage point, a place to observe humanity without confronting humanity, Mars would be ideal. Mars also provides a quieter environment. Earth's orbit is surrounded by satellites, its skies crowded with aircraft, its surface buzzing with activity. By contrast, Mars is silent. Its only residents are machines, rovers, crawling across dusty plains, orbiters mapping the surface, and landers that sit patiently, listening. These machines do not question, do not resist, do not defend. They simply record and transmit. To an outside intelligence, that might make Mars an appealing perch. A world that already hosts instruments, but where those instruments belong to us, not to them. Beyond practicality, there is symbolism. In human culture, Mars has always been the other world. It is close enough to matter, yet distant enough to feel alien. We see it as both neighbor and frontier, a place we could one day call home, but not yet. In this sense, Mars is already a middle ground, not Earth, not entirely alien, but something in between. An interstellar visitor passing close to Mars steps directly into this symbolic space, bridging the familiar and the unknown. From a scientific standpoint, Mars is also intermediate in habitability. It is not lush like Earth, but it is not completely hostile like Mercury or Pluto. It has just enough atmosphere to tempt us, just enough history of water to intrigue us. Yet it lacks the protective blanket of Earth's magnetic field, leaving it exposed. For humans, this makes it a challenge. For observers, it makes it a laboratory, a world balanced between promise and peril, preservation and decay. The idea of Mars as middle ground also extends to time. Earth's biosphere is vibrant now, but it has been stable only for a few billion years. Mars, by contrast, carries records from a more ancient era, frozen into rocks that have barely changed since their formation. To study both together is to see a spectrum, Earth in full bloom, Mars as a fossil of what might have been. An interstellar probe near Mars would not only monitor Earth's present, but also glimpse echoes of Earth's possible future. Does this mean 3I, Atlas, chose Mars deliberately? Science says no, its path is a product of gravity, not intention. Yet the alignment remains powerful. Mars is neither too close nor too far, neither too crowded nor too empty. It is, in every sense, a middle ground. And if meaning can be found in coincidence, then perhaps this is the meaning of Atlas's passage. To remind us that the most interesting perspectives often come not from the center, but from the margins. In the balance between Earth and the stars, Mars stands as a quiet witness, and in October 2025, so will 3I, Atlas. When we picture Mars, one color comes to mind: red. The red planet is covered in dust laced with iron oxides, minerals that scatter sunlight in rusty hues. From orbit, its deserts glow with ochre tones. From the surface, its skies often appear salmon or orange, stained by suspended grains. This redness is more than a visual trait, it is a fingerprint of the planet's geology, a reminder that chemistry and color are inseparable. So, when telescopes captured the coma of 3I, Atlas, and noted a reddish tinge, the comparison to Mars was immediate. Here, too, was a body whose light seemed filtered through iron dust, glowing faintly with a Martian palette. Two very different worlds, one a planet, the other a comet-like interstellar visitor, yet both dressed in the same color. Could this be coincidence? Or does the redness reveal a deeper kinship between Mars and Atlas? The answer begins with dust. Every comet, whether from our solar system or beyond, sheds particles as sunlight heats its surface. These grains scatter light, giving the coma and tail their characteristic glow. The composition of the dust determines the color. In most comets, the result is a bluish-white haze, the reflection of silicates mixed with water ice. Atlas, however, showed something different, a warmer, redder hue. To scientists, this suggests that its dust is rich in complex organics or iron-bearing minerals, the very compounds that dominate Mars's surface. On Mars, the iron story is well understood. Billions of years ago, water interacted with basaltic rock, oxidizing iron minerals. Over time, the planet dried, leaving behind layers of rust-colored dust. Winds carried this dust across the globe, coating everything in shades of red. Atlas may have experienced a parallel process, though on a smaller scale. If its surface contained iron-rich silicates, then exposure to cosmic radiation during its long interstellar journey could have altered them, oxidizing iron and reddening its grains. The result? A reddish coma, echoing Mars' rusty deserts. There is another factor. The thinness of Mars's atmosphere allows dust to linger, suspended for months during global storms. On Atlas, the coma itself acts like an atmosphere, a cloud of particles hovering around the nucleus. In both cases, sunlight filtering through this haze enhances the red tones. Thus, Mars and Atlas are not only chemically similar, but visually alike, two bodies defined as much by dust as by rock. For astronomers, this resemblance is not proof of connection, but it is striking. Color, after all, is one of the first impressions we form of a world. We call Mars the red planet not because of its gravity or orbit, but because of the way it looks to the eye. Atlas, drifting through the solar system, has earned a similar description: a reddish wanderer, an interstellar twin of Mars's dusty complexion. Speculation, of course, pushes further. Could the redness itself be a kind of marker, a feature meant to draw attention? If an advanced intelligence wished to disguise a probe, what better camouflage than to echo the appearance of a planet we already study obsessively? Mars-colored dust would seem familiar, natural, even comforting. The parallel could be coincidence, but coincidence with symbolic weight. Even without speculation, the geological mirroring matters. If Atlas carries iron oxides, then it tells us something about the environments where such minerals form. It suggests that the chemistry leading to red worlds may be common across the galaxy. Mars may not be unique in wearing the color of rust. There may be countless planets, moons, and comets glowing red beneath distant suns, shaped by the same dance of rock, water, and time. Why does Atlas look Martian red? Because dust remembers. It remembers chemistry, radiation, and history. It remembers the environments that shaped it. Just as Mars's dust tells the story of a once wet planet turned dry, Atlas's dust tells the story of interstellar wandering, of iron and organics weathered by ages in the dark. Together, they stand as geological twins, not identical, but resonant, each reflecting the other in color, chemistry, and symbolism. Color is not just appearance. In astronomy, color is chemistry, and chemistry is history. When we look at Mars, its red face tells us of ancient processes of iron, water, and time, conspiring to stain a planet with rust. And when telescopes turned to 3I, Atlas, and detected a reddish hue in its coma, the similarity was hard to ignore. Two very different bodies, one a planet, the other an interstellar traveler, yet both dressed in the same dusty shade. On Mars, the explanation for redness is well known. Its surface is littered with iron-bearing minerals, primarily in basaltic rock. Long ago, when liquid water flowed on the planet, these minerals oxidized. Instead of metallic iron or dark basalt, chemical reactions produced hematite and other iron oxides. Once Mars lost its thick atmosphere and its water receded, winds took over. They ground rocks into fine grains and carried them across the globe, creating a planet-wide blanket of rust. The result is the familiar crimson desert we see today, a world painted by its own geological memory. For Atlas, the story is more mysterious, but perhaps not entirely different. Comets and small bodies shed dust as they approach the sun, and this dust is what creates the glowing coma and tail. Most comets in our solar system scatter sunlight in grayish or bluish hues, a reflection of silicates and icy grains. But Atlas displayed a warmer tone. The data suggest its dust may contain iron-bearing compounds, or complex carbon-rich organics. Either pathway leads to a reddish glow, reminiscent of Mars. Radiation is also a player. Atlas has likely spent millions of years drifting through interstellar space, its surface battered by cosmic rays. Over time, radiation can alter the chemistry of exposed ices and minerals, reddening them by breaking molecular bonds and leaving behind darker iron oxide-like residues. A process that takes eons in the deep void may have produced the same effect that water and atmosphere once achieved on Mars. Different mechanisms, similar outcomes. A red body born of exposure and endurance. The resemblance goes deeper than color. Both Mars and Atlas tell stories of transformation through loss. Mars lost its water and became dry. Atlas may have lost much of its water ice, leaving carbon dioxide and oxidized dust behind. Both wear their scars in red. In this sense, color becomes metaphor. It is the visual language of survival under harsh conditions. To planetary scientists, such parallels are intriguing. If Mars and Atlas both bear iron oxide signatures, it suggests that the chemistry leading to red worlds may not be rare. Perhaps the galaxy is dotted with planets and comets that share this hue, worlds oxidized by water, by radiation, or by both. Mars may be just one local example of a universal theme. The cosmos paints in rust. Of course, speculation lingers. To human eyes, similarity invites meaning. Some wonder whether the redness of Atlas is coincidence or communication, a natural comet that happens to look like the very planet we obsess over. To observers seeking patterns, the mirroring feels uncanny. Mars, our neighbor and ambition, and Atlas, a visitor from another star, both glowing in the same spectral shade, both demanding our attention. The safer answer is chemistry. Dust explains Mars. Dust explains Atlas. But coincidence can still resonate. When two distant stories rhyme, we take notice. Mars and Atlas remind us that color is more than beauty. It is a record of processes written on surfaces, a clue carried across millions of years and millions of kilometers. Why do they both look red? Because dust remembers. It remembers the water that once carved Mars's valleys. It remembers the radiation that sculpted Atlas in the dark. In that shared memory, two very different worlds appear as twins, geological echoes of each other bonded not by origin, but by the universal chemistry of iron, oxygen, and time. Space is patient. Objects wander for millions of years, drifting between stars with no urgency. But human science is not patient. We live in windows opportunities that open for weeks, sometimes days, before closing forever. When 3I, Atlas, was discovered, astronomers realized that one such window was about to open. On October 3, 2025, the object would pass within 29 million kilometers of Mars. For the first time in history, an interstellar body would come close enough to be studied not only from Earth, but from another planet's orbit. For NASA, the timing was both a blessing and a challenge. A blessing, because the red planet was already surrounded by a fleet of orbiters. A challenge, because none of them had been designed to study an interstellar comet. Instruments built to monitor weather, map rocks, or sniff for methane now needed to be retasked quickly for an entirely new kind of target. The Mars Reconnaissance Orbiter, MRO, launched in 2005, became the centerpiece of this scramble. Its high-rise camera, with resolution sharp enough to see rover tracks, was repurposed for a far more distant job, capturing faint images of Atlas against the black sky. The Chrism spectrometer, though partly degraded, could still collect light at multiple wavelengths, offering a chance to identify gases streaming from Atlas's coma. Even the Marcy weather camera, usually tasked with watching Martian dust storms, was evaluated for long-exposure tracking. Other orbiters were called into action too. MAVEN, with instruments designed to study how solar wind strips Mars's atmosphere, could monitor energetic particles interacting with Atlas's gases. The European Trace Gas Orbiter, built to detect methane in Mars's thin skies, offered sensors sensitive to faint chemical signatures. Together, these spacecraft formed an improvised observatory, hastily coordinated across agencies and continents. Why scramble? Because interstellar opportunities are vanishingly rare. Before Atlas, only 2 such visitors had ever been confirmed: Oumuamua in 2017 and 2I, Borisov in 2019. Both slipped away before we could prepare. Oumuamua was already leaving the solar system by the time it was noticed, its bizarre cigar-like shape sparking endless debate but offering little data. Borisov, though better observed, passed closer to the Sun than Mars, and telescopes struggled to capture its details. Atlas, by contrast, offered something new: an extended encounter near a planet already swarming with our machines. The geometry made the urgency clear. From Earth's perspective, Atlas would be lost in the Sun's glare during its closest approach. Ground-based telescopes could not watch. Even Earth-orbiting observatories like Hubble were at a disadvantage. Only Mars had the right angle. Only Mars's orbiters could record what Earth could not. To miss the chance would mean losing forever the opportunity to compare an interstellar body's behavior up close. Behind the scenes, this scramble revealed another truth: the adaptability of science. Missions like MRO and MAVEN had been operating for years, some well past their original lifespans. Their teams had spent decades refining routines, pointing instruments at predictable Martian targets. Now, suddenly, they were asked to reprogram commands, recalibrate sensors, and prepare for observations no one had planned. The excitement was palpable. To study Mars was expected. To study the galaxy from Mars was not. Still, expectations were tempered. Atlas would not blaze across Martian skies like a second Sunday. To orbiters, it would appear as a faint dot, dimmer than many stars. Success would mean capturing even a handful of frames showing its coma, or detecting spectral hints of its gases. Yet in science, even faint dots can change our understanding. A spectrum recorded in October 2025 could tell us about chemistry forged in another star system billions of years ago. The scramble, then, was not panic but opportunity. NASA and its partners understood that the cosmos rarely aligns in our favor. When it does, we must act quickly. And so, as Atlas drifts closer to Mars, orbiters stand ready, silent witnesses prepared for a task no one imagined when they were launched. In years to come, the Mars flyby may be remembered less for what it revealed than for what it symbolized. Humanity's readiness to adapt, to stretch old tools toward new horizons, and to seize moments when the universe opens a narrow door. When we think of seeing, we think of human eyes. But in astronomy, our truest vision comes from machines, sensitive to wavelengths we cannot perceive, capable of exposures longer than any blink. They translate the language of light into data we can understand. In the story of 3I, Atlas, 2 such machine eyes stand out. HiRISE aboard the Mars Reconnaissance Orbiter and the James Webb Space Telescope orbiting near Earth. One gazes outward from Mars, the other peers across deep space. Together, they serve as translators between a wandering fragment of another star system and the curiosity of our species. HiRISE, the high-resolution imaging science experiment, is one of the most powerful cameras ever flown beyond Earth. Designed to map Mars in extraordinary detail, it can resolve objects less than a meter across on the planet's surface. It has captured avalanches tumbling down slopes, dust devils twisting across plains, and even the descent of rovers under parachutes. Yet its abilities extend beyond geology. With careful programming, HiRISE can point away from the ground and toward the heavens. In October 2025, during Atlas's closest pass, it may do just that, turning its gaze outward to try to capture a faint, moving dot against the backdrop of stars. What HiRISE lacks in light-gathering power, it makes up for in precision. Its ability to fix on a target and record consistent data could allow scientists to measure Atlas's brightness over time, detecting subtle variations. Those flickers may reveal whether Atlas rotates, tumbles, or erupts with jets of gas. Though the images may not show detail, they will still carry meaning. Like notes on a score, each pixel can be interpreted, turned into evidence about a body born far away. On the other side of the system, the James Webb Space Telescope has already begun its study. In August 2025, JWST trained its golden mirrors on Atlas and split its light into spectra. The result was startling. Carbon dioxide emissions 8 times stronger than water vapor, a chemical imbalance unlike anything in familiar comets. JWST could not see Mars, but it could see Atlas's chemistry, providing the context for what HiRISE and other orbiters might glimpse later. If HiRISE provides motion and brightness, JWST provides language, the vocabulary of molecules, the grammar of photons. Together, they complement each other. JWST's immense sensitivity, shielded from the sun by its vast sunshade, is like a deep listener straining to hear whispers across interstellar distances. HiRISE, in orbit around Mars, is like a vigilant sentinel, noting presence and change at a moment when Earth itself is blinded by sunlight. Neither could tell the story alone, but together they create resonance. Chemistry paired with geometry, detail paired with context. This dual vision reveals another truth. Machines extend us. No human eye will ever look directly at Atlas from Mars. No astronaut will raise binoculars beneath the Martian sky in 2025. But our machines will. They are our translators, our extensions into environments we cannot reach. They take the silent photons of a comet and turn them into data, into graphs, into knowledge. In this sense, they are not passive tools. They are active intermediaries between the cosmos and our imagination. There is poetry in this. Two machines, built for very different purposes, end up entwined in the same story. One was built to study a planet. The other was built to study the universe. And now, through coincidence, both converge on the same object, a traveler from another star. Their combined observations will not only inform science, but also remind us that the act of seeing is always collaborative. Human intention, machine precision, cosmic chance, each plays a part. When historians of astronomy look back on 2025, they may not remember the raw numbers of brightness, curves, or spectra. They may remember instead the symbolism that when an interstellar wanderer swept near Mars, Earth and Mars both looked up, not with human eyes, but with machine ones, and those eyes, steady and patient, became translators of the unknown. On Earth, the approach of 3I, Atlas, in October 2025, brings frustration as well as excitement. For much of its closest pass, the object will sit in the glare of the sun as seen from our planet. Telescopes, no matter how powerful, cannot look into that brightness without being blinded. Even space-based instruments like Hubble are constrained by geometry. In practical terms, Earth enters a period of radio silence, unable to see, unable to measure, forced to wait while a once-in-a-lifetime event passes just beyond reach. But silence on Earth does not mean silence everywhere. In fact, at the very same moment Earth is blinded, Mars is positioned at a different angle, offset just enough in its orbit to see what we cannot. And circling Mars are a handful of spacecraft not designed for this role, but capable of it nonetheless. This raises a striking possibility that the real listening post for Atlas may not be Earth at all, but Mars' orbit. Consider the geometry. At closest approach, Atlas will pass within 29 million kilometers of Mars. That is still distant, yet far closer than it will ever come to Earth. From orbit, instruments aboard the Mars Reconnaissance Orbiter, MAVEN, and the European Trace Gas Orbiter can attempt to gather data. Their sensors, pointed usually at Martian skies, can be turned outward. What Earth cannot see through glare, Mars can see against the blackness of space. In a way, this shifts the balance of roles. For centuries, Earth has been the seat of astronomy, the platform for every great telescope. But in this case, Earth is sidelined, and Mars, or at least our machines there, becomes the privileged observer. It is as though the cosmos has rearranged the stage, granting Mars the microphone while Earth sits in the dark. This creates a symbolic resonance. Mars, the planet we dream of colonizing, becomes in this moment our eyes and ears. Its orbiters act as relay stations, recording what our own world cannot. For a brief span of weeks, Mars is not just an object of study, but also a participant in astronomy. It is transformed into a forward base for interstellar science. There is also a speculative layer to this. Some have wondered whether Mars has always been the better vantage point, not just for us, but for anyone observing Earth. Its orbit is near enough to monitor our electromagnetic leakage, yet far enough to remain unnoticed. Its skies are quiet, unpolluted by human technology. If one wanted to study Earth discreetly, Mars' orbit would be ideal. And now, by coincidence or fate, 3i, Atlas will pass closer to Mars than to us. From a purely scientific perspective, this means better chances of gathering data. The orbiters may capture faint spectra, brightness variations, or even compositional hints we would otherwise miss. From a symbolic perspective, it feels like a role reversal. Earth, blind; Mars, watchful. For the first time, astronomy becomes truly multiplanetary, with one world doing what the other cannot. And there is poetry in the silence itself. While Earth waits, Mars listens. While Earth is overwhelmed by light, Mars sits in shadow. Our machines, drifting high above the Martian surface, become proxies for our curiosity. They listen for whispers in the dark, turning silence into signal, absence into presence. Will they succeed? No one can say. Atlas is faint, and the orbiters were not built for this task. But even the attempt matters. It demonstrates adaptability, the willingness to treat every alignment as an opportunity. It shows that astronomy is no longer bound to Earth, but can extend wherever we place instruments, and perhaps that is the larger lesson. Radio silence on Earth does not mean ignorance. It means we must learn to listen differently, through other vantage points, through other worlds. In October 2025, Mars becomes that vantage point, not only a planet to explore, but a partner in exploration, a listening post for the universe itself. To human eyes, Earth seems like the obvious focus. It is alive, noisy, and bright with signals. Radio waves leak into space. Cities sparkle on the night side. Spectroscopy of our atmosphere would reveal oxygen, methane, and water vapor, the unmistakable fingerprints of biology. If an interstellar probe like 3i Atlas were sent to study the solar system, surely Earth would be the main target. And yet, in October 2025, Atlas passes closer to Mars. Why Mars first? The simplest explanation is geometry. Atlas follows the path set by gravity, not intention. Its course happens to bring it within 29 million kilometers of Mars, while Earth remains hidden in the glare of the sunday. The encounter is an accident of orbital mechanics, not a deliberate choice. From a strictly scientific standpoint, that is all we need. But curiosity drives us to ask a second question. If this were intentional, what logic might favor Mars over Earth? The answer may lie in indirect observation. When humans explore, we rarely rush straight to the most important target. We orbit first. We observe from a distance. We map, measure, and test before risking a landing. The Voyager probes flew by planets without touching them. The Galileo and Cassini spacecraft orbited giant worlds, studying moons and atmospheres long before we dreamed of sending landers. The logic is simple. Safety and perspective come first. For an intelligence studying Earth, Mars would be the ideal indirect vantage point. From Mars's orbit, Earth can be monitored continuously, its signals recorded without interference. The separation, about 55 million kilometers at closest approach, is close enough for sensitive instruments to detect our broadcasts, yet far enough to remain unnoticed. Mars provides both distance and access, a balance that Earth itself cannot offer. There is also the matter of environmental contrast. To understand a system fully, scientists often study its extremes as well as its center. Mars is Earth's neighbor, similar in size and history but vastly different in outcome. Where Earth thrives, Mars withered. Where Earth's atmosphere is thick, Mars is thin. Where Earth is blue, Mars is red. By observing Mars first, an outside intelligence could establish a baseline, a control case against which Earth's uniqueness can be measured. To study Earth without studying Mars would be like reading one page of a book and ignoring the rest. Another logic is stealth. Earth is crowded with watchers. Telescopes scan the skies daily. Radar tracks thousands of satellites and asteroids. A probe approaching Earth too closely might be noticed. Mars, however, is quiet. Its only inhabitants are machines we ourselves placed there, machines that dutifully send data home, but cannot question what they see. For an observer wishing to remain hidden, Mars offers discretion. From there, they could study both Earth and Mars without alerting us to their presence. Even from a symbolic perspective, Mars holds appeal. It is the planet humanity dreams of colonizing, the stepping stone to becoming interplanetary. By focusing on Mars, an observer could be looking ahead as much as looking across, studying not just who we are but who we intend to become. Earth tells the story of life as it island. Mars tells the story of life as it might be fragile, experimental, on the edge of habitability. So if they wanted Earth, why Mars first? Because Mars offers perspective, safety, and subtlety. It provides the comparative data needed to interpret Earth's signals. It offers a listening post far from suspicion, and it mirrors Earth's past and possible future in ways that make the two planets inseparable. The scientific consensus will remain with geometry. Atlas' path is coincidence, not choice. But coincidence can still feel like strategy. To us, the encounter suggests a lesson. Sometimes, to understand the heart of a system, you begin not at the center, but at the margins. You start with Mars. Mars today is a desert. Its skies are thin, its winds weak, and its rivers long since vanished. But the planet's rocks whisper of another era. Billions of years ago, Mars was warmer and wetter. Valleys carved by flowing water, minerals formed in lakes, and deltas shaped by long-lost seas all tell the same story. A planet once capable of supporting conditions closer to Earth's. Mars, in its youth, may have been blue, not red. Now, imagine an object drifting in from another star system, 3I Atlas, whose chemistry seems oddly familiar. It exhales carbon dioxide in extraordinary proportions, overwhelming water vapor by 8-to-1. To modern Mars, this echo is obvious. Today, the Martian atmosphere is 95% CO2. But what if the resonance goes deeper? What if Atlas is not only similar to Mars as it is now, but also reflective of conditions Mars once knew, conditions locked away in time? To explore this idea, we must think of both Mars and Atlas as time capsules. Mars preserves its past in stone. Its craters and canyons are archives of epochs when water shaped the land. Its minerals remember chemistry long erased from the atmosphere. Each rover that drills into its rocks uncovers fragments of a climate that disappeared eons ago. Atlas, by contrast, preserves its past in ice. Formed in a different star system, it has carried its frozen inventory across interstellar space, largely unaltered for millions of years. Where Mars is a geological memory, Atlas is a chemical one, and their stories rhyme. Mars lost its water as its atmosphere thinned, leaving carbon dioxide as the dominant gas. Atlas may have lost water too, not to atmospheric escape but to radiation and cosmic exposure during its long journey. Over time, the delicate balance of volatiles shifted, and CO2 emerged as the survivor. Both bodies, though worlds apart, arrived at the same state: carbon dioxide abundance, water scarcity, and a chemistry that speaks of decline as much as of origin. The comparison raises profound questions. Could Atlas represent the fate of Mars-like planets elsewhere? Perhaps the galaxy is full of such bodies, worlds that begin with rivers and seas, only to lose them, leaving behind a legacy of CO2. If so, then Mars is not an outlier, but part of a larger pattern. Its transformation from habitable to hostile may be a common planetary arc. Atlas, drifting in from afar, would then be a messenger of that truth. There is also a subtler layer. Some of Mars's most intriguing features: subsurface ice, briny pockets beneath polar caps. Hints of methane plumes suggest that traces of habitability may persist even after the main climate collapses. Could Atlas carry similar traces from its origin world? Organic molecules frozen in its ice, preserved as fossils of chemistry from long ago. If so, Atlas is not only a time capsule of environment, but also of possibility. A fragment that tells us not just what was lost, but what might once have been alive. Speculation lingers at the edges. If Atlas were not natural, but a probe disguised as cometary debris, then echoing Mars's current state might be a deliberate choice, a way of speaking to us in a familiar dialect. But even without intention, the resonance feels meaningful. Mars lost its water billions of years ago. Atlas lost its water across interstellar time. Both now carry the same signature: a world, or a fragment of one, that remembers what was once possible. In the end, the question is not whether Atlas literally reflects Mars's past. It is whether their shared chemistry tells us something about how planets evolve, how environments are lost, and how fragile habitability can be. Mars shows us that a world can change within a single solar system. Atlas reminds us that such changes echo across the galaxy. Together, they are time capsules, one geological, one chemical, whispering the same lesson through different languages of memory. As 3i Atlas continues its fleeting journey, Mars spins silently on, its deserts glowing under a cold Sunday. Maybe this was just chance, a rock from another star brushing past a world we already loved. Or maybe, hidden in orbital geometry and chemical echoes, there lies a deeper purpose. Either way, the question remains, drifting across the void. What does 3i Atlas want with Mars? The answer, like so much in astronomy, may never arrive. But sometimes, the question itself is enough to fill our nights with wonder.